This is Mrs. Palmer-Quay with the second video for the Measurements and Units module. In this video, I want to talk about accuracy and precision in your measurements and how you identify the significant figures in a measurement. There's always some uncertainty in a measurement. We don't know how reliable the measuring tool was. Were the marks on the meter stick accurately placed? Was the balance calibrated? This causes some question on how accurate the results are, how close it is to the true value. And there's also uncertainty about the skillfulness of the person doing the measuring. Do they know how to operate whatever tool they're using? Are they focusing on reading the numbers correctly? So that when we're dealing with accuracy and precision and talking about significant figures, we're recognizing that there's uncertainty. We're not exactly perfectly true on all of our measurements. The words accuracy and precision are used in common language often to represent basically the same thing. But when it comes to science, they do mean two different things. Accuracy reflects how close the measurement is to the accepted value or the true value. What is the real amount for how long something is, how much mass something has, how much volume is in of a particular fluid. How close your measurement is to what the true value is how accurate you are. How precise you are reflects how close the measurements are to each other. We can think of that as how small is the unit that is in the measuring scale. So a measuring tool that has very small units can give you more precision than one that has bigger units, and we'll see this on the next slide. So these bull's eyes give you 4 examples of where accuracy and precision can be very different in a measurement. The first measurement here, trying to hit the bullseye, there's definitely low accuracy. Those darts are nowhere near the center, and they have low precision. The individual darts are not very close to each other. So this is not a measurement that you really can trust. It is neither accurate or precise. This second one has low accuracy. Again, it's not near the bullseye, but it has very high precision, that they're all very close to each other. They keep on getting the same place. The darts are hitting the same place, or the same measurement comes up, but it's not near the true value or the accepted value. This kind of a situation can be seen when your instrument has not been calibrated, so you've got this serious error because the measurement tool itself is off somehow, or the person doing the measuring is making the same mistake over and over again. This third example has high accuracy. The darts are all into the bullseye there, but fairly low precision. They're not very close to each other. This third bullseye is what tends to happen in lab. Lab group 1 gets this value, lab group 2 gets this value, and the third lab group gets that value. And so this is why we are often taking group results and taking an average of the 3 in our class before we do some calculations with the numbers. Because one of the things that you can do is if you average many results, you can see that averaging these 3 values will get you closer to the center of the bullseye. But of course, what you're striving for is this fourth one, where you have both high accuracy and high precision. You're hitting the right value, and your repeated readings are very, very close together. The book does not discuss percent error, but we do these calculations in lab, so I wanted to include it. Percent error reflects how accurate the measurement is when you have a known value or an accepted value. And so you're comparing your experimental value, or sometimes you see this written as measured value, with the known value or the accepted value or the true value. In order to figure the percent error, you take the experimental value and the known value and calculate the difference between the two. And so you're subtracting one from the other. It really doesn't matter what order you do it in because you do have these as absolute values, so there would not be any negative sign. And you take that difference and divide it by the known value and multiply it by 100. So then you're going to get a percent. The percent error, if it's a small number, it's saying that your value is accurate. It's very, very close to the known value. If it's a larger number, well, then your number is way off what the accepted true value is. So percent error is a calculation that you will be asked to do in lab. Significant figures will be plaguing you for the rest of your chemistry career. Every time you do calculations and make measurements, you need to think about the number of significant figures in your measurement, and then when you calculate it, you need to express your answer with the correct number. We'll talk more about calculations in the next video. This time I just want to start by talking about what is a significant figure. The definition of a significant figure is that it is all the certain digits, all the numbers that you are certain about in a measurement, plus one that you're not quite so certain about, or maybe you had to estimate it, which is just a reflection of your uncertainty because you had to estimate. The number of significant figures is affected greatly by the precision of your measuring tool, how much the space that you're measuring in has been subdivided. So we have 3 different measuring tools shown here, and this is just sort of, I'm trying to measure this red rectangle. You know, where does it, if I'm using these 3 measuring tools, what am I reading as this value here on the final edge? My first measuring tool just goes between 0 and 1. And so I really only have one place, one number to work with, and I'm going to have to just guess, okay, if 0 is over here, and these aren't lined up particularly well, but let's say 0 is over here, well, yeah, let's see, you know, we kind of subdivide this. This is about 2/3 of the way up, so we're going to say that it is 0.6. Usually we'd write that as 0.6. But we are only able to write one figure here, and it's definitely something that's uncertain or estimated. There's only one significant figure that's even possible using this measuring tool. In this second measuring tool that's here in the middle, we see that the end of my rectangle is somewhere in between the 6 and the 7. So I know it is 6 something. It is at least 6, whatever this unit is, centimeters or meters. And it's not quite 7, so I'm going to be estimating this next piece. And so it doesn't look like it's part halfway. So let's say that it's, 6.4. So my 6 is my certain number. The 0.4 is my uncertain number. And then down here on this final measurement, you can see that we're pretty clear that we've got 6 or 6D, and yes, it is coming down to that little line that would make it 4, and then the uncertain or the estimated point is between these 2 lines of what would be 64 or 65. So we're going to say that it's 64, my 2 certain numbers, it's 0.1 maybe, it's just over the line. Or if I was certain that it was right on that line, I would say 0.0, showing that I was able to make one estimated number along with these 2 that I am certain about. So that the significant figures is reflecting how precise you can be in your measurement and is only giving you one estimated digit. I wouldn't take this second one, for example, and say that it was 6.4279 because that has more estimated digits than 1. It has 3 extra estimated digits that should not count. So that you want to be careful when you have a calculator not to have too many significant figures. Just because it shows up on the calculator doesn't mean you can report it. So to identify significant figures, there are some rules. The first rule is that all non-zero numbers are significant. That is abbreviated significant figures as sig figs here. So 237 has 3 significant figures. And then any 0 that's in between non-zero numbers is significant as well. So in 39,004, it has 5 significant figures. 2.05 has 3 significant figures. Then you have zeros that are on the right end zeros. If there is a decimal point present in the number, then those zeros are significant. So 620.0 has 4 significant figures, and 19,000 written with a decimal point at the end has 5 significant figures. This last one is not used by your textbook, but you may see it as you move on in science. And so if there is a decimal point, every right end zero is significant. Figures that are not significant include your left end zeros and right end zeros for numbers without a decimal point. Left end zeros, or in both of these cases, zeros are serving as placeholders. So if our 0.008, the 8 is the only significant figure. The other ones there are just holding places to let you know that we are moving, or we are measuring in the thousandth position. 140 has two significant figures. The 1 and the 4 are significant. The 0 is here just as a placeholder saying that there was nothing in the 1's position. The next video will talk about calculating with significant figures and how to then write the answer with the correct number of significant figures. I won't necessarily take 50% off if you don't have the correct number of significant figures, but especially on tests, if you give me too many, you're going to be losing parts of points. So that finishes what I want to say in this second video.